So now we would like to discuss how do we evaluate this integral? Well, notice here, we're basically doing the Fourier transform of a function that only depends on p dot p. So it only depends on the magnitude of p. At the moment, we are integrating over the, at the moment we are integrating over the px, py, and pz components of momentum. So I now want to change variables, and this is motivated because basically the integral that I'm doing is the Fourier transform of something that only depends on the magnitude of p. And I want to introduce the magnitude of p. Okay, so, p would just be the magnitude of p, and then two angles as usual, a theta and a phi. And let's talk about this integral in a little bit of detail. Let's evaluate it together. So we're going to have an integral dp, dp times by p squared. This integral will run from 0 to infinity. We will have an integral d phi, which goes from 0 to 2 pi, and we'll have an integral d theta sine theta, and the integral d theta sine theta runs from 0 to pi. Then we've got the 1 over 2 pi cubed, so let's put in the 2 pi cubed, and we've got an e to the minus I square root of p squared plus m squared times by t plus I, and p dot x is p times the mod of x. So I'm going to call the mod of x to be r. So we'll have r, and then we've got cosine of theta. A dot b is the mod of a times the mod of b times by the cosine of the angle between the two vectors. Okay, so this is the integral that I would like to evaluate. Good. So the integral over phi is rather trivial. Nothing in the integrand depends on phi, and that was the statement that the integrand only depended on the magnitude of p. So our payoff for this change of variables comes in the fact that the integral over phi is so easy. We've got a p squared. We no longer have the integral over phi. We still have an integral d theta from 0 to pi. The integral over phi has given us a factor of 2 pi, so we get sine theta over 2 pi squared. Okay, so the 1, 2 pi coming from the integral over phi has cancelled one of the 2 pi's and the 2 pi cubed, so we've now only got 1 over 2 pi squared. And then we have e to the minus I square root of p squared plus m squared t plus I pr cosine of theta. Okay, now how do we do the theta integral? Well, something that's worth noting is d cos theta is minus sine theta d theta. So if I was to say u is cos theta, okay, then what you can see is du would be minus sine theta d theta. And that's good news because that's exactly what I've got appearing in the integrand. I've got a d theta sine theta, so I can just change that into a du. Now, of course, when theta is equal to 0, that corresponds to u is equal to 1. And when theta is equal to pi, that corresponds to u is equal to minus 1. So the way the integral is written, the integral from 0 to pi is an integral from 1 to minus 1. But remember, I've got a minus sign because du is minus sine theta d theta. So I can use the minus sign from du to swap the limits of the theta integral so that it goes from minus 1 to 1. So if I make those steps, what do I get? Well, let's just clear a little bit of space here. Good. So we will have, this is equal to an integral from naught to pi dp times p squared, an integral du from -1 to 1 over 2 pi squared. And then we have an e to the minus I square root of p squared plus m squared t plus I p r u. And you see, the nice thing now is the integral over u is very easy to do because we're just integrating an e to the IPRU. By the way, for all of these steps, I expect that you can do manipulations like this in your sleep. So if you struggle at all, please make sure you can do it. Oh, I noticed 2 typos, so that shouldn't be a pi. That shouldn't be a pi. Let's correct those. That should be infinity. That should be infinity. You should constantly be checking me because I can make a lot of mistakes. So this now becomes an integral from naught to infinity, dp, p squared. Then we'll have a 1 over 2 pi squared. The integral of e to the IPRU with respect to u will give us a 1 over IPR. And then we just need to evaluate the integrand between u as 1 and u is equal to -1. So let me pull this exponential out, minus I square root of p squared plus m squared t. And then we have, so let's say multiplied by e to the IPR, that's when I plugged u is equal to 1, minus e to the minus IPR. And I just have a single integral left to do. Now that integral can actually be done analytically, and you would get an answer in terms of Bessel functions. Now, unless you naturally remember the asymptotic behavior of Bessel functions, that answer will not be very useful to you. So what you're going to do in the homework problem of this week is you're going to evaluate this integral approximately. And so you're going to evaluate approximately. So evaluate approximately. And you're going to do that using a method, which goes under the name of the saddle point approximation. Sometimes people call it the stationary phase approx. So stationary, so this should be stationary phase approximation. And the reason why I want you to do that is that this approximation can be used all over the place when you'd like to know how an integral behaves. So it's an extremely useful approximation technique to master. So in the set of problems that you'll solve this week, I've guided you through that. So how do you do the final integral over p approximately? I've guided you through that process. What I would like to do now is just tell you what the answer looks like, okay? Now, let's remember, what are we interested in checking? Well, we wanted to check, so the question we want to ask is, can our particles move faster than light? Okay? And remember, our particle traveled from x is equal to 0 to position x in a time t. So, another way to ask this question is, does our probability amplitude vanish when is greater than t. The biggest distance that light can travel in a time t would be a distance t, because c is equal to 1. So the question is, can we travel a distance r which is larger than t? And that would correspond to our particles traveling faster than the speed of light. And what we find when we evaluate this amplitude is that this amplitude does not vanish. In fact, what we find is, so let's call this P. So for our probability amplitude, maybe I'll call it prob. What we find for our probability amplitude is that prob is equal to some number, which you will calculate, and then you've got e to the minus m, the square root of r squared minus t squared. So if r is bigger than t, this probability is not 0. If you make r very much greater than t, it goes to 0 exponentially fast, but the probability is not 0. And that means our particles really can travel faster than light, and we found a problem with our theory.